Lesson: Basics of Reinforcement Learning. Reinforcement learning represents a critical area in the intersection of artificial intelligence and cybersecurity. It is a type of machine learning where an agent learns to make decisions by performing actions in an environment to maximize cumulative rewards. Unlike supervised learning, which relies on labeled data, RL is driven by interactions and feedback from the environment. This paradigm is particularly suitable for cybersecurity applications, where dynamic and adaptive responses are essential to address evolving threats. RL operates on the principle of trial and error, where the agent explores various actions and learns from the consequences of those actions. The core components of RL include the agent, the environment, actions, states, rewards, and a policy. The agent interacts with the environment, which is typically modeled as a Markov decision process. At any time step, the agent observes the current state, takes an action, and receives a reward along with a new state from the environment. The goal of the agent is to learn a policy, a mapping from states to actions, that maximizes the expected cumulative reward over time. One of the foundational algorithms in RL is Q-learning, a model-free technique that does not require a model of the environment. Q-learning aims to learn the quality of actions, represented by the Q function, which estimates the expected utility of taking a given action in a specific state and following the optimal policy thereafter. The Q value is updated iteratively using the Bellman equation, which incorporates the immediate reward and the discounted future rewards. The update rule is given by call galpha Q minus Q. Where is the learning rate? Is the discount factor? Is the reward? Is the current state? Is the action taken? And is the next state? Deep reinforcement learning extends traditional RL by incorporating deep neural networks to approximate the Q function or the policy. This approach has been highly successful in complex, high-dimensional environments, such as playing Atari games or defeating human champions in Go. DRL can be particularly advantageous in cybersecurity, where the state and action spaces are large and complex. In the context of cybersecurity, RL can be applied to various domains, such as intrusion detection, malware analysis, and network defense. For instance, in intrusion detection systems, RL can be used to dynamically adjust detection thresholds or to adaptively deploy countermeasures in response to detected threats. Traditional IDS often rely on static rules or signature-based detection, which can be easily circumvented by sophisticated attackers. RL-based IDS, on the other hand, can learn from the environment and improve their detection capabilities over time. An example of RL in intrusion detection is the use of DRL to detect and mitigate distributed denial-of-service attacks. DDoS attacks involve overwhelming a target system with a flood of traffic, rendering it unavailable to legitimate users. Traditional mitigation strategies, such as rate limiting or IP blacklisting, may be insufficient due to the evolving nature of the attack. By employing DRL, an IDS can learn to identify patterns of malicious traffic and take adaptive actions to mitigate the attack while minimizing the impact on legitimate traffic. Another application of RL in cybersecurity is in automated malware analysis and classification. Malware authors continuously evolve their techniques to evade detection, making it challenging for static analysis tools to keep up. RL can be used to dynamically analyze and classify malware by interacting with the malware in a controlled environment and observing its behavior. For example, an RL agent can execute the malware in a sandbox environment, monitor its actions, and learn to classify it based on the observed behavior. This approach allows for the detection of previously unseen malware variants and can adapt to new attack strategies. Network defense is another critical area where RL can be leveraged. In a typical enterprise network, defenders must continuously monitor and protect a vast number of devices and communication channels. RL can be used to automate and optimize the deployment of defensive measures, such as firewalls, intrusion prevention systems, and access control policies. For example, an RL agent can learn to deploy firewall rules dynamically in response to detected threats, optimizing the trade-off between security and usability. By continuously interacting with the network environment, the RL agent can adapt to changing threat landscapes and improve the overall security posture of the network. One of the challenges in applying RL to cybersecurity is the exploration-exploitation dilemma. In RL, exploration involves trying new actions to discover their effects, while exploitation involves selecting actions that are known to yield high rewards. In a cybersecurity context, excessive exploration can lead to unintended consequences, such as triggering alerts or disrupting normal operations. Conversely, excessive exploitation can result in suboptimal performance, as the agent may not discover better strategies. Balancing exploration and exploitation is crucial for the successful application of RL in dynamic and adversarial environments like cybersecurity. Another challenge is the sparsity and delayed nature of rewards in cybersecurity. Unlike gaming environments, where rewards are frequent and immediate, cybersecurity scenarios often involve sparse and delayed feedback. For example, the consequences of deploying a particular defense strategy may not be immediately observable, making it difficult for the RL agent to learn from its actions. Techniques such as reward shaping, where intermediate rewards are provided to guide the learning process, and temporal difference learning, which can handle delayed rewards, are essential to address these challenges. Despite these challenges, the potential benefits of RL in cybersecurity are substantial. By leveraging RL, cybersecurity systems can become more adaptive, resilient, and effective in countering advanced threats. The ability to learn from interactions and continuously improve decision-making capabilities aligns well with the dynamic and evolving nature of cyber threats. As RL algorithms and techniques continue to advance, their application in cybersecurity is expected to grow, offering new opportunities for enhancing cyber defense. In conclusion, reinforcement learning represents a powerful approach for addressing the challenges of cybersecurity. By enabling systems to learn from interactions and adapt to changing environments, RL can enhance the detection, analysis, and mitigation of cyber threats. The application of RL in areas such as intrusion detection, malware analysis, and network defense demonstrates its potential to improve the effectiveness and resilience of cybersecurity systems. As the field of RL continues to evolve, its integration into cybersecurity strategies will play a crucial role in defending against sophisticated and dynamic cyber threats.